Load flow analysis, also known as power flow analysis, represents one of the most fundamental studies in power systems engineering. This steady-state analytical method enables engineers to calculate critical operating parameters including bus voltages, voltage angles, real and reactive power flows throughout electrical networks, equipment loading levels, and system losses under specified operating conditions. The primary engineering objective is to determine whether transmission networks, distribution feeders, substations, industrial facilities, or renewable energy interconnection points can operate safely within acceptable voltage and thermal limits. Rather than serving merely as a computational exercise, load flow analysis constitutes a complete modeling workflow that encompasses system definition, iterative solution, and engineering judgment to validate operational acceptability. The significance of load flow analysis extends far beyond its individual results, as it establishes the foundational steady-state operating case upon which virtually all other power system studies depend. Fault studies, voltage regulation analyses, stability assessments, contingency evaluations, interconnection studies, and equipment upgrade decisions all commence from a trusted load flow solution that accurately represents the system's normal or planned operating condition. Understanding this central role underscores why engineers must approach load flow studies with rigorous attention to model accuracy, data validation, and result interpretation. To navigate load flow studies effectively, practitioners must master essential terminology that appears consistently throughout software outputs and technical discussions. Buses represent the fundamental nodes where generators, loads, transmission lines, transformers, and reactive power devices interconnect. These connection points serve as the locations where voltage magnitudes and angles are calculated. Branches encompass the lines, cables, and transformers that electrically connect buses together, carrying power flows that determine loading levels and voltage drops. Injection refers to the net power balance at any bus, calculated as generation minus load consumption, where positive values typically indicate power entering the network while negative values represent demand. Mismatch quantifies the difference between specified and calculated power quantities during the iterative solution process, with convergence achieved when mismatches fall below specified tolerances. The slack bus, also called the reference bus or swing bus, provides the angle reference for the entire network and absorbs the cumulative effect of system losses and any residual power imbalances. The load flow study workflow follows a systematic three-stage process that transforms raw system data into actionable engineering insights. In the first stage, engineers construct a comprehensive network model by defining all equipment parameters, topology, and operating assumptions including load levels, generation dispatch, and device statuses. The second stage employs numerical solution methods that iteratively calculate unknown quantities until power balance equations are satisfied within acceptable tolerances. The third stage involves thorough review of results against project-specific criteria for voltage limits, thermal ratings, reactive power capability, and loss thresholds. This workflow emphasizes that successful load flow analysis requires not just mathematical convergence but also engineering validation that the solved operating point represents a realistic and acceptable condition. Central to understanding load flow methodology is recognizing that different buses play distinct roles based on which quantities are known versus unknown. Three fundamental bus types govern this classification: slack buses, PV buses, and PQ buses. The slack bus serves as the system reference, with voltage magnitude and angle specified as known quantities while real and reactive power output remain unknown and determined by the solution process. PV buses, typically representing generator terminals or voltage-controlled devices, have real power output and voltage magnitude specified while reactive power and voltage angle are calculated. PQ buses, most commonly representing load centers, specify both real and reactive power demand while solving for resulting voltage magnitude and angle. This classification framework determines how the system of nonlinear power flow equations is structured and solved, making it essential knowledge for anyone conducting or interpreting load flow studies. The slack bus, functioning as the reference point for the entire power system model, anchors the voltage angle reference conventionally set to 0 degrees while maintaining a specified voltage magnitude typically near nominal value, often 1.0 per unit or slightly higher such as 1.04 per unit to account for voltage drop in the system. Unlike other bus types where power injections are specified, the slack bus absorbs whatever real and reactive power imbalance remains after solving all other buses, effectively balancing system losses and compensating for any small numerical discrepancies in the converged solution. This characteristic makes the slack bus output an important diagnostic indicator. Unrealistically high slack bus generation or absorption often signals data errors, unrealistic operating assumptions, or disconnected equipment in the model. Engineers typically locate the slack bus at the strongest grid connection point or largest generator, reflecting the physical reality that major generation sources or utility tie points naturally assume the balancing role in actual power systems. PV buses represent voltage-controlled points in the network, most commonly corresponding to synchronous generators, utility-scale inverters, or other devices equipped with automatic voltage regulation capabilities. At these buses, the engineer specifies the target real power output based on economic dispatch or operational requirements along with a desired voltage magnitude set point. The load flow solver then calculates what reactive power injection and voltage angle are necessary to achieve these targets given the surrounding network conditions. However, an important practical consideration limits this behavior. Every voltage controlling device possesses finite reactive power capability bounded by generator rating curves, inverter specifications, or equipment thermal limits. If the solution requires reactive power beyond available capability, the PV bus transitions to PQ behavior with reactive power fixed at its limit and voltage becoming a solved quantity rather than a controlled set point. This mode switching behavior, automatically handled by most commercial software, reflects physical reality and significantly impacts voltage profiles in stressed system conditions. PQ buses constitute the most numerous bus type in typical power system models, representing load centers, distribution substations, and other locations where power demand is the primary defined quantity. Engineers specify both real power consumption in megawatts and reactive power demand in megavars at each PQ bus, typically derived from load forecasting, metering data, or planning scenarios. The load flow algorithm then calculates what voltage magnitude and phase angle result at each PQ bus given the specified demand and the surrounding network state. These solved voltages provide crucial information about system health. Voltages substantially below nominal indicate excessive voltage drop, possibly requiring corrective actions such as capacitor switching, transformer tap adjustment, or conductor upgrading. Conversely, unusually high voltages during light load conditions may indicate excessive reactive compensation or inappropriate tap settings. Because PQ bus voltages emerge from the solution rather than being directly controlled, they serve as sensitive indicators of overall system conditions and model accuracy. Building a reliable load flow model requires careful attention to multiple input data categories, each affecting different aspects of the solution. Bus data defines the network nodes including identification numbers, nominal voltage levels, type assignments, voltage set points for controlled buses, and operational limit constraints. Load data specifies the demand characteristics including real and reactive power magnitudes, power factor, load models, constant power, constant impedance, or combinations, operating scenarios such as peak or light load conditions, and diversity factors for aggregated loads. Generator data captures output schedules, voltage control settings, reactive capability limits, and operating status for all controllable sources. Line and cable parameters include resistance, reactance, and charging susceptance that determine power transfer characteristics, voltage drop, and losses, along with ampacity or thermal ratings that define acceptable loading limits. Transformer data encompasses impedance values, MVA capacity ratings, winding voltage ratios, tap positions and ranges, and phase shifts for regulating transformers. Shunt device data covers capacitor banks, reactors, and other reactive compensation equipment with their switching status and MVAR ratings. The quality of input data fundamentally determines solution reliability. The most sophisticated solver cannot produce meaningful results from inaccurate or incomplete model information. The core mathematics underlying load flow analysis derives from AC circuit theory expressed through complex power relationships and the bus admittance matrix formulation. Complex power injected at any bus equals the product of bus voltage and the conjugate of current entering the bus, with positive values indicating generation into the network and negative values representing load consumption. Current at each bus relates to all bus voltages through the admittance matrix, whose elements capture the electrical connectivity of lines, transformers, and shunt devices throughout the network. Diagonal admittance matrix terms sum all admittances connected to each bus, while off-diagonal terms represent the direct electrical coupling between specific bus pairs. This mathematical structure creates coupled nonlinear equations relating voltage magnitudes and angles to power injections, necessitating iterative numerical solution methods since no closed-form algebraic solution exists for practical systems. A simple 3-bus example illustrates the complete load flow problem setup and interpretation. Consider a system with bus 1 designated as slack with voltage specified at 1.04 per unit and angle fixed at 0 degrees, requiring solution for resulting real and reactive power output. Bus 2 operates as a PV bus with 100 megawatts generation scheduled and voltage target set at 1.02 per unit, leaving reactive power and angle to be determined. Bus 3 represents a PQ load consuming 80 megawatts and 35 megavars, with voltage magnitude and angle emerging from the solution. Upon convergence, if bus 3 voltage solves to 0.92 per unit, the engineer must evaluate whether this level satisfies project criteria considering equipment ratings, customer requirements, and regulatory standards. Similarly, if the line connecting bus 2 to bus 3 operates at 112% of its thermal rating, the case fails despite acceptable voltages, potentially requiring redispatch, reconfiguration, or facility upgrades. This example reinforces that mathematical convergence alone does not guarantee engineering acceptability. Professional judgment must always supplement computational results. 3 principal numerical methods dominate load flow solution practice, each offering distinct advantages suited to particular applications. Gauss-Seidel iteration provides conceptual simplicity ideal for educational contexts and very small systems, updating voltages sequentially using the most recent values available. While straightforward to implement and understand, Gauss-Seidel converges slowly for large networks and may fail entirely on heavily loaded or weakly interconnected systems. Newton-Raphson iteration achieves superior convergence performance by simultaneously solving for voltage corrections using a Jacobian matrix that captures sensitivity of power mismatches to voltage changes. This method forms the workhorse of commercial power system software, reliably handling large transmission and distribution networks with robust convergence characteristics despite greater computational complexity per iteration. Fast decoupled load flow exploits the physical property that real power depends primarily on voltage angle while reactive power depends mainly on voltage magnitude, enabling simplified calculations that dramatically reduce computation time for large systems. This approximation works well for high-voltage transmission networks with low resistance to reactance ratios but loses accuracy when applied to distribution systems with significant resistance or weak voltage support. Selecting the appropriate solution method depends on system characteristics, study objectives, and practical considerations. Small teaching problems benefit from Gauss-Seidel's transparency in demonstrating iterative mechanics without obscuring the process behind sophisticated algorithms. General engineering applications across transmission and distribution systems typically default to Newton-Raphson for its proven reliability and broad software support. Large-scale transmission planning studies involving thousands of buses may employ fast decoupled methods when the decoupling assumptions hold, achieving faster solutions for scenario sweeps and contingency analyses. Distribution systems with higher/X ratios, weak voltage support, or unbalanced configurations require either full Newton-Raphson treatment or specialized distribution power flow formulations designed for radial network topologies. When encountering convergence difficulties, experienced engineers first scrutinize model data quality before changing solution methods, recognizing that non-convergence frequently indicates problems with input data, topology errors, or physically infeasible operating scenarios rather than algorithmic limitations. Interpreting load flow results requires systematic evaluation across multiple dimensions, not merely confirming solver convergence. Voltage profile assessment identifies buses operating outside acceptable ranges, whether excessively low indicating inadequate voltage support or unexpectedly high suggesting possible data errors or inappropriate compensation settings. Line loading review flags circuits approaching or exceeding thermal ratings, particularly under contingency conditions where single component failures shift flows onto remaining paths. Transformer loading examination verifies that power transformers operate within nameplate capacity and approved emergency ratings, considering both normal and post-contingency conditions. Reactive power flow analysis evaluates whether generators, capacitors, and other reactive sources provide adequate local support without excessive transfers that increase losses and reduce margins. System loss assessment quantifies total real and reactive power losses, identifying high-loss branches that may warrant investigation for optimization opportunities. Slack bus output verification. Verification confirms that reference generation or absorption falls within reasonable bounds, with anomalous values triggering data quality reviews. A genuinely healthy load flow case satisfies all these criteria simultaneously, meeting project-specific requirements rather than merely achieving mathematical convergence. Modern load flow analysis leverages diverse software platforms ranging from comprehensive commercial suites like ETAP, PowerWorld Simulator, PSS/E, and DIGSL Power Factory to open-source tools such as OpenDSS and Python libraries including PandaPower. Despite interface differences among these tools, the underlying engineering workflow remains consistent, constructing the one-line diagram model with accurate representation of buses, branches, transformers, and shunt devices, entering detailed electrical parameters including impedances, ratings, tap positions, and base values, assigning appropriate bus types reflecting actual operating roles, selecting relevant operating cases spanning peak load, minimum load, future expansion, distributed energy resource export, and outage contingencies, executing the solver until convergence within specified tolerance, and comprehensively reviewing all outputs against engineering criteria. Contemporary power systems incorporating solar photovoltaics, battery storage, and inverter-based resources introduce additional complexity requiring careful attention to export conditions that may reverse traditional power flow directions, reactive power capability modes that differ from synchronous machines, and voltage control behaviors that vary with inverter technology and settings. A case appearing normal under peak load conditions may behave radically differently during midday solar production with light native load, necessitating scenario-appropriate analysis. When load flow solutions fail to converge, the symptom itself provides diagnostic information pointing toward likely causes and remedial actions. Immediate divergence upon solution initiation typically indicates fundamental data problems such as missing slack bus assignment, isolated network islands created by open breakers or disconnected topology, or severely erroneous parameter values. Progressive voltage collapse in specific geographic areas suggests heavy loading overwhelming available transmission capacity combined with insufficient local reactive power support, prompting review of load assumptions, capacitor bank status, generator reactive limits, and transformer tap positions. Generators hitting reactive power limits may indicate overly aggressive voltage setpoints or inadequate local reactive resources, requiring examination of PV to PQ transition behavior and available capability curves. Extremely high branch flows often traced to impedance data errors, incorrect tap position entries, misapplied ratings, or topology mistakes that create artificially low impedance paths. Cases converging only with relaxed tolerance settings suggest weak system conditions or unresolved data issues warranting investigation of mismatched distributions rather than acceptance of degraded accuracy. Throughout troubleshooting, maintaining focus on model fidelity proves more productive than algorithm manipulation, as convergence on an inaccurate model provides false confidence in meaningless results. Common pitfalls in load flow practice stem more frequently from procedural oversights than mathematical errors, making awareness of these patterns valuable for practitioners. Selecting inappropriate load cases represents a fundamental error, as peak load, light load, emergency, and future expansion scenarios produce meaningfully different voltage profiles, loading patterns, and loss levels. The chosen case must align with the specific engineering question being addressed. Neglecting transformer tap positions ignores their substantial influence on voltage profiles across different voltage levels and along lengthy feeders, necessitating confirmation of actual field settings and testing of alternative positions during sensitivity analysis. Treating convergence as approval constitutes perhaps the most dangerous mistake, as mathematically converged solutions may still exhibit unacceptable voltages, overloaded equipment, violated reactive limits, or excessive losses that render the case unsuitable for decision-making regardless of solver status. Forgetting reactive power limitations allows optimistic voltage control assumptions that physical equipment cannot achieve, requiring explicit checking of Q-limit violations in PV to PQ conversion events. Skipping contingency analysis examines only the intact network configuration, potentially masking vulnerabilities that emerge when individual components fail. Reliability-focused studies must include N1 and sometimes NK outage cases. Finally, relying on stale operating assumptions introduces discrepancies between modeled and actual conditions as transformer taps drift, capacitor banks switch out of service, load patterns evolve, and distributed generation alters traditional flow paths. Regular reconciliation with field data maintains model credibility over time. The overarching principle guiding sound load flow practice holds that engineers should never terminate analysis upon observing solver convergence. Instead, comprehensive result review should systematically verify voltage adequacy across all buses, thermal headroom on all branches and transformers, reactive power reserves at all controllable sources, loss levels consistent with expectations, slack bus outputs within reasonable bounds, and overall consistency with physical intuition about system behavior. Only after passing this multi-dimensional validation should results inform engineering decisions regarding system design, operation, or investment. Load flow analysis, properly understood and executed, transcends mere calculation to embody a complete engineering discipline integrating theoretical knowledge, modeling skill, numerical methods literacy, and professional judgment. Its mastery enables power systems engineers to confidently assess existing infrastructure performance, plan future expansions, integrate new technologies, and maintain reliable electricity delivery within technical and economic constraints. As power systems evolve toward higher renewable penetration, smarter grid technologies, and more complex operational paradigms, the foundational importance of sound load flow analysis only increases, making competence in this area indispensable for modern power engineering practice.